you so much for taking the time to join our webinar and tutorial, Multi-Point Design and Optimization of Hybrid Electric Aircraft Engines, presented by Michael Seeleman, Modelon's Aerospace Industry Director, and Modelon Application Engineer, Maden Joy. My name is Jocelyn Pazlowski, Modelon's Marketing Director, and I will be the moderator. Today, our webinar and demo will cover aircraft engine design of conventional and hybrid electric aerospace engines using the multi-point design approach. During the second portion of the demo, we will provide access to the live web app, and this will be linked in the chat window. Today's presentation will last roughly 60 minutes, and we will have about 10 to 15 minutes available for Q&A at the conclusion of the presentation. The Q&A button is at the bottom of your screen, so please feel free to submit your questions during or after the presentation. A link to view the webinar on demand will be available and emailed in coming days. And I am now happy to turn the mic over to Michael.
Thank you, Jocelyn, and also welcome from my side. So before we start, I want to highlight that this is a technical webinar. If you're interested in a more general overview, we also have some on-demand webinars, such as the general Modelon Impact Introduction or Modelon Impact for Aerospace. So if you're interested in that high-level summary, go check those out. They're available on our webpage. Here, we want to start with something that is familiar with, that everybody is familiar with, namely classic cycle design. So the classic on-design performance problem is shown here. What the user wants to compute and find out is this component sizing here. In order to do this, we must define design choices such as your compressor pressure ratios, component limits such as your maximum temperatures, and also the flight conditions, so your altitude, your day type, etc. And then as outputs, we get the performance parameters and this component sizing information. The component sizing info can then be used to fire off any number of off-design performance problems. And here the user essentially wants to feed in other flight conditions and find out the performance for those. And the component sizing here in the middle, this is really an umbrella term for whatever parameters describe the physical design or the physical sizing of all the components of the system. And based on what model fidelity you're using, this can be simple map scaling factors, streamline curvature, flow path, geometry, or many other things. But from the cartoon on this slide, we can already see the key limitation. The design can only be defined by a single operating condition. And this is a rather strong limitation of this classic approach. And that's what we remove with the modern multi-point design. So in high level, multi-point design is really about making information flow both ways between design point and the off design points. And we label this reverse flow of information here, design choices 2, because the framework then allows us to impose any targets from the off design points for efficiency, for performance. So you can specify your specific thrust or jet velocity ratio on one of your off design points through this multi-point approach. For comparison, we also list pros and cons of the classic and of the multi-point approach in this and the previous slide. But these are for your reference only, and I will not talk through them. Instead, let's create a simple multi-point synthesis for a turbojet. And yeah, on the left, you can see the scope of the plant model that we're considering. We essentially model a single spool turbojet and then add cooling and customer bleed on top of that. And for now, we will simply use the views, the graphical interface of Modelon Impact as our graphical notation. And for the turbojet model, you see the airflow here through the compressor burner turbine with the orange connections. You can also see the black connections for the mechanical spool and cooling and customer bleed here. So it's really just looking like a set of interconnected components at this point. Then for the multi-point synthesis, we need to introduce those different cases that we want to look at. So you see here rolling takeoff, top of climb, and our nominal cruise condition. And we do that by introducing an additional hierarchy level. So we essentially introduce one level above what we just saw on the previous slide. And now each of the engine icons here, they really represent one of different cases that we're looking at. And this is then called instantiation. And we link the sizing of these engines together and expose all three sizing and operation inputs on this level. So those are your compressor design pressure ratios, fuel flows, etc. that we mentioned before. And then we just started introducing the coupling between the different cases. So in this example, we find the overall pressure ratio in design. That would be this guy here, based on the overall pressure ratio in one of the off-design cases. So this is cruise. This is done through this block and that connection. We select the overall airflow in design based on combustor outlet temperature, again in a suitable case, cruise here. And of course, we also discover the fuel to air ratios based on the net thrust. So that's an operation variable. So the triangles here, these connectors are orange in our convention, and we can define those for each of the points because yeah, we can operate the engine there at different operating conditions. And lastly, we need to solve for the cooling flow from a target in terms of the uniform blade temperature. So this is really the metal temperature of your cooled blades. How hot can it be? From that, we deduce how much cooling flow we need. And with this, we already have our first simple multi-point synthesis for this turbojet. Now let's scale this up to the complexity of a typical gear turbofan as they're flying today on modern commercial aircraft. And for that, we're going to review two academic state-of-the-art schemes. The first one that you see here came out of Cranfield University and was applied for quite a range of conventional, unconventional aero engine cycles. You can already see the graphical notation here to the right. So in terms of noteworthy aspects here, the design bypass ratio here in the top of climb design point is imposed by a target in jet velocity ratio, and this goes back to the theory of Guha. Then, as we saw it before, there is a design point overall pressure ratio that we find based on an overall pressure ratio target in cruise. So this is this connection here, but this has to be expanded then because overall pressure ratio is really the product of all the individual fan and intermediate high pressure compressor pressure ratios. So we use the pressure ratio exponent within this block here to solve that analytically in line with the Cranfield scheme. Then the design point fan pressure ratio is found based on a target here in specific thrust. That is again applied for efficiency on the nominal cruise case. And yeah, all the other boxes here for net thrust and turbine cooling, those closure equations are really similar to the ones that we used for the turbojet example already. And yeah, all of this together then yields the Cranfield multi-point scheme. So far, we've used the graphical notation to describe and illustrate these design schemes. Now, if any of you reads or writes scientific publications in this area, you may also find one alternative notation useful, these synthesis tables. And they really describe these important closure equations defining the multi-point synthesis. So this portion down here, if you're interested in understanding those, what do you need in terms of terminology? It's not much. There are really just two terms that they introduce. It's fancy labels really for model inputs and model outputs. So the first one, the synthesis variables are really just model inputs and arbitrarily selected by the modeler. And these target variables here, they're really just model outputs that the modeler may want to fix or prescribe in one way or another. So I brought a few examples of these variables. There are two tables here. First one has examples of synthesis and target variables for operation. The other one for sizing. And here this example for fuel flow. People typically use as synthesis variables the model inputs fuel to air ratio or dimensional fuel flow in kilogram per second or pound mass per second, whatever you prefer, and targets such as net thrust or combustor outlet temperature. And here is the first synthesis table. This one's for this grand field scheme that we just reviewed. And the way this works is that we first introduce columns for the cases in the operating envelope. So you see these acronyms here, top of climb, rolling takeoff, and nominal cruise. First one's supposed to be the design point. And then as rows, we list all the target variables in the sizing and the operation categories. And below that, we list all the synthesis variables. So these were the model inputs, those were the model outputs really. And here's one important piece to notice for the synthesis variables and the sizing category. The cells span all the different columns because the sizing cannot change obviously from one operating condition to another. So there's really just one variable for all of those cases together. And the key information in these synthesis tables is really defined by keywords. There are three different keywords. The first one is fixed. That's used for synthesis variables only. And that means that the value of that synthesis variable is known and it's entered by the user. Second keyword can also be used only for synthesis variables, and it's just variable as we see here. And that means that the synthesis variable value is not known, but it's actually modulated iteratively by the numerical solver. And lastly, we have this keyword target here. Target can only be used for target variables, and it means that the target is known and used as some threshold in the residuals of the solver. And if a cell is empty, then, well, we can compute the values from the governing equations, but it really means that there are no closure equations describing the values of these cells. So a lot of detail, but in simple terms, the synthesis tables, they really just say vary this variable or that set of variable until we're satisfying all the outputs listed up here. So as we then saw before, just going through some of the cells here for this grand field scheme, the overall pressure ratio and the pressure ratio exponent that we talked about, they're satisfied by varying the low pressure and the high pressure compressors in the design point. And the design point fan pressure ratio is found based on this target and specific thrust and so on. So hopefully you can see some of the elements that we discussed in the graphical notation also in these synthesis tables. There is a second academic state-of-the-art multi-point scheme that we mentioned here. That's from NASA Glenn originally. We will just cover that quickly in the scientific notation here. The table, I actually split that into two parts because of the screen space. So this part to the right here is really the top portion with the outputs that we're prescribing, and the bottom part is here in the middle with the inputs that we're varying. And yeah, you can probably also see that there is a fourth column that they introduce for sea level static. And there are also some additional entries related to variable area fan nozzle. I've colored them in gray, so you can ignore them if you want to focus on conventional engines only. The first main feature here is again the use of a jet velocity ratio as a target. This time it's not ideal, and it's the inverse of the one suggested by Guha. And yeah, the synthesis variable is again the bypass ratio in design. Second feature is related to overall pressure ratio. In the original version that I put on the slide here from NASA Glenn, they assume that the fan pressure ratio and the low pressure compressor pressure ratio at design are fixed. You can see this in the dash boxes here. And therefore we can go directly from our target and overall pressure ratio to the design point pressure ratio for the high pressure compressor. And we don't need any pressure ratio exponent or things like that. The only difference here in terms of the overall pressure ratio is that they prescribe this for the top of climb case instead of the nominal cruise as we saw for the Cranfield scheme. The last and probably neatest feature that I want to highlight here on the Glenn scheme is how they define the synthesis variables and targets for the burner outlet temperature and the net thrust across several cases. So they start with defining the combustor outlet temperature here in rolling takeoff. This is entered by the user. And then the corresponding value in top of climb is defined by a multiplier that they call the thrust lapse requirement. And therefore, the net thrust for top of climb is really prescribed implicitly only through this combustor outlet temperature. But then they take this value and again apply a multiplier, 90% of that as target for the nominal cruise condition. And the only case in the operating envelope and the corner points, if you will, that they consider in their multi-point synthesis, the only point with a dimensional thrust target here is rolling takeoff. And then from rolling takeoff, they again take a multiplier as the target for the sea level static net thrust with this multiplier that they call the equivalent thrust multiplier. And then, yeah, we see right away, we have 5 thresholds that we're fixing, and we have 5 independent synthesis variables. So this part of the computational problem is also square, and we can define all the thrusts and burner outlet temperatures from these equations. And this already concludes the overview of the NASA Glenn scheme. So lastly, let's take a quick look at the hybrid electric Aero engines. And for that, we will discuss a boosted turbofan, which is also known as a parallel hybrid. And yeah, in essence, that's the simplest way to yield an electrified Aero engine. We take a gear turbofan and bolt on an electric drive with all its power subsystem and a thermal management subsystem to dissipate all the excess heat. And you can see some of the key components here on the schematic. One of the benefits is that the powertrain is still relatively simple. simple to install, simple to analyze in comparison to some of the other more involved concepts, such as using boundary layer ingestion. And yeah, the community has discussed, I believe, at least 4 different variants of this parallel hybrid. So the one that we're talking about here is the first variant shown here. Now, obviously, if we want to do an integrated design of such systems, we also need to expand the scope of the physical plant model such that we include all the other subsystems that we want to cover in the integrated design. And the schematic here shows how we include the electrical power system, for which we use Modelon Impact's electrification library, and an analytic design procedure for that. So I hope you can see the electric machine, some cables, inverters, battery here. Then for the Aero engine, so the gas turbine portion of this, on the multi-point synthesis there are probably 2 key ways to define closure equations on the multi-point synthesis. This first one is really just the prescription of electrical boost power via explicit closure equations and the additional synthesis variables down here, low pressure spool shaft power. And the other alternative approach is to introduce these boost power synthesis variables as free variables and imposing additional temperature ratio targets. And yeah, both approaches have their pros and cons with respect to robustness, uniqueness, cycle theory. So ensuring that we compare apples to apples, and more detail is available in the literature on that. Due to the available time, we go right into some results. You can see here that we're varying the specific thrust of the parallel hybrid. And this is a key cycle parameter for the propulsive efficiency. As we go to low values, we end up with a low fan pressure ratio and a very high diameter fan that reduces the losses in the wake of the engine and therefore yields more efficient engines. And you can see here to the left a cut view or a flow path of such an engine. This is for a specific value of the specific thrust that you can see up here. And then we looked at different installation options for the electric machine within such engines. So the one that we see here has the electric machine right inside the intermediate pressure compressor. So the rectangles that you see up here and down there are representing the rotor and the stator of the electric machine. And then as we vary the specific thrust, we can look at cycle performance results, both for the gas turbine portion or the electric subsystem. So we will vary this x-axis here with different values of specific thrust and the target value changing here. And then we can observe what that change implies to the estimated efficiencies, the estimated component masses that we see at the bottom. So on the left, you can see how the engine's becoming smaller or bigger as we go back and forth. And here we see gearbox masses, electric machine masses, estimated intermediate pressure, high pressure turbine masses, and so on. So this is already the theory that we covered today, and there were a lot of acronyms and methodology. And I hope that you got along well. When we send out the link to the recording of the webinar, we will also include a write-up if you're interested in some of the terms and some of the theories, such the Guha reference. Yeah, check that out and you find the references there. So with that, Mithun, are we ready for the demo?
Yes, Michael, thank you. Let me take 1 second to share my screen. Can you guys see my screen now?
Yep, I see.
Thanks, Michael.
On presenting mode.
That's okay, since I have to go into Impact soon. So just to quickly introduce myself, my name is Modelon. I'm an application engineer at Modelon. And for the next 30 minutes, I'll be demoing some of the concepts that Michael just covered in the last half an hour. So before I dive into the actual demo, just want to give you an overview of what we will be looking at. So we'll start with a simple turbojet model, and we'll look at the classic cycle design approach for it. And in the classic cycle design, we'll look at our on-design and off-design simulations. So our design point here is going to be sea-level static conditions, and we'll also simulate the model in a couple of off-design cases, so rolling takeoff and top of climb, for example. Then we'll take the same model, but look at it from the multi-point approach point of view. So the starting point will be the same model, but we'll be looking at the multi-point approach there. After that, we'll look at a slightly more complicated turbofan model, and then again, look at the multi-point or modern cycle design approach. And finally, we'll look at the turbofan model from a web app, just showing some of the collaboration capabilities of Modelon Impact. So with that, I'll open Impact, which I'm accessing through Chrome here. And in the interest of time, I've already done some preparation work. And what you see on the canvas here is a typical turbojet model. All of these components have parameters that can be defined. For example, here we have the compressor, where we can specify our pressure ratio design and polytropic efficiency and so on. One specific component that I want to highlight here is the ambient block. And this is basically the block where we can input our flight conditions. So if you see here, we have three parameters, the altitude, the temperature difference with respect to the atmosphere, and the Mach number. And those are our flight conditions. I also want to highlight two other parameters here that are quite important for this workflow. So the first one is a flag called use PBS, where PBS stands for physics space solving. And this parameter here is a hint to the compiler, the Modelica compiler behind Impact. And it's essentially telling it whether it should look at annotations in the Modelica code and use those to identify variables to iterate on and variables to hold. And the second parameter that I want to highlight here is on design. It's again a Boolean flag. And just like the name suggests, this would be used to control whether we simulate our model in design conditions or off design conditions. So with that said, we have our model already parameterized for our design point, which is again sea-level static conditions. So all the three parameters here should have values of 0, and I'm going to keep it that way. And once we've defined our model setup, we can move into the experimentation mode. I'm going to minimize this tab here. And then jet propulsion has some functions that enable the modern cycle and the classic design cycle workflows. So I'm going to utilize this function. So one argument that this function takes is a string, and this string is basically going to be the name of a file with sizing information for our model. So if you remember from the slides, that sizing information from our design point will be input to the off-design simulations. So I'm going to specify SLS here for sea-level static. And with that, I have my experimentation or my simulation setup complete. And I can simulate by just clicking on the simulate button here. So the first step here is to compile the Modelica source code into a binary algorithm. We use something called FMUs, and the FMUs and the algorithm in that is then solved for by the solver. And after the simulation is done, we get our results. And now we have our result mode here with a result file, which I can rename. And I'm going to rename this to SLS for sea level static again, just to easily identify it. And before looking at some variables, I want to go back to my simulation mode and simulate our off design conditions, a couple of those. So the first thing I want to do is turn the on design flag off. And you can see that now we're in off design mode. And the first off design condition I want to simulate is rolling takeoff. So I specify a reasonable Mach number, 0.25. And then I again go to my experiment mode. I want to keep this the same because I want to use the sizing information from our design point. And so everything looks good here. I can simulate my model again. And now we have a second result file here, which I'll rename to RTO for rolling takeoff. And I'll go back and simulate one more off design case. And this is a good time to highlight a capability in Impact called views. So we can have views with widgets that expose some key parameters of variables. And these widgets, we call them stickies. It's a convenient way to input parameters instead of opening this toolbar on the right. So you can see that my 3 flight condition parameters, altitude, delta temperature, and Mach number are available here. And I can input values for those into these fields here. So the next off design case I want to simulate is climbing condition and say an altitude of 5,000 feet, but I see my units here as in SI, so I can go into settings and just quickly change that to imperial. I can also select from available choices in the imperial system. So I'll change a couple here and then I can save that. So now I can input my altitude in feet. And again, if I go to my experimentation mode, I keep everything the same here and I simulate the model again. Note that the second off design simulation here did not require a recompilation. And now I have a new result file, which I will call climb 5K. And now we can look at some key results. So I'll disable my case setup view and enable a view that I already saved with some important variables populated as stickies. So if we start with our on design simulation, we can see that the pressure ratio and the speed for the compressor are exactly what we specified. And now if I look at running takeoff, it's changing. And then finally for the climb case, it's again changing. And we can see that the shaft speed here is actually higher than what we specified for the compressor's shaft speed. And this is obviously not good. And this is suggesting that we need some kind of control logic to limit the compressor shaft speed. So the next step here would be to enable or add that control logic. And in the interest of time, I've again done that for you. So here, if I look at the baseline model, this is exactly what we just simulated. But with the controls added, the model is going to look something like this. So I can explain the differences here. So we have a control block that controls the burner fuel input through fuel to air ratio. And that fuel to air ratio is calculated based on a specified value for the combustor or the burner outlet temperature and the compressor shaft speed ratio with respect to the design speed. We also added 3 bleed flows here. So the first 2 are to the turbine for cooling the turbine blades. And then we also have a third bleed flow for customer needs. The next step here would be the same. So we simulate the model in on and off design. And again, in the interest of time, I've already done that here. And if we look at the results, we have our on design simulation at static level, sea level static conditions, and we have 3 off-design simulations here. Let's again look at some of the results. I'll enable my view. So here, our sea level static conditions have exactly what we input as a parameter because that is our design point simulation. And if we look at our running takeoff, we can see that the value is changing. But if we look at the climb 5K and the top of climb cases, the shaft speed for the compressor is now limited to the design speed we specified. So that is an overview of the classic cycle design approach. And one important takeaway here is that changing or targeting variable values in off-design conditions is not straightforward. So as an example, say in top of climb conditions, you wanted the pressure ratio to be 7 instead of 6.97. How would you do that in the classic cycle design? You would go back into your on-design conditions, change your parameter input, simulate the model in the design and off-design conditions again, look at the value. If it's good, you got lucky. If it's the same, if it's the target value, you got lucky, but typically that process takes a few iterations, and that kind of manual work is cumbersome. And this is exactly where the multi-point or modern cycle design approach is very beneficial. It really tells the solver to take care of that iteration for you, so you don't have to do it manually. So our starting point for the multi-point workflow is the same. So we start with single point simulations and obtain results for a few cases. And then the next step is to expose all the synthesis or input variables that we want to control externally to the top level. So here we can see that there are 4 variables exposed to the top level, 2 in orange and 2 in blue. So the orange ones here are the operation synthesis variables. We have a fuel to air ratio input and also the fractional bleed flow fractions. So those are the 2 operation inputs or synthesis variables. And then we also have 2 sizing inputs. So the flow rate for the air, as well as our overall pressure ratio. And one important thing to note is that the sizing is only applicable in the design case. So these 2 connectors or inputs should only show up for our on-design simulation. And I can verify that by opening the code editor here. And if I look at lines 9 and 10, we can see that those sizing inputs are conditional based on ambient.onDesign, which is the flag for telling whether a model is being simulated in on-design or off-design mode. So now that we have the submodel, this model that's going to be used to generate our multi-point instances, we can again utilize a function available in the Jet Propulsion library, where we can specify names for our on-design submodel. So this can be, for example, SLS again for sea level static, and also off-design submodel. Here, cruise could be our off-design submodel. And then the function also lets you save the generated model at a specified path. Here we are saving it in a subpackage called multi-point, and the model name is called generated. And there's also the flag here to override any existing models. So I've already done this. And if I look at my multi-point package here, I have a model called generated. And what you see here is exactly what would be the output from running that function for generating the submodels. So here we have our on-design submodel called SLS and our off-design submodel called CRZ for cruise. And you can also see that the sizing inputs, which are blue in color, are only shown in the on-design submodel. Now we can utilize these submodels and connect them up with closure equations to really control our inputs or our synthesis variables. And here is an example for that where if we look at one of the control blocks, it's for the overall pressure ratio. So we're targeting a value of 6 in the cruise conditions. Again, once I've defined this control logic, I can specify, by the way, I can specify whatever value I want to target here as a parameter for any of these blocks. And once I've done that, I can move to the experimentation tab and then use another function in jet propulsion to simulate this model in multi-point mode. Just a quick note that this function is only needed the first time you simulate a multi-point model. And the reason or the logic behind that is that you want to make it easier for the solver to converge to the solution by providing previous result files from our single point simulation. So specifically, if you look at the parameter value here, we are pointing it to the control model, which would be our source for the single point results. And then we're also mapping our submodel instances to result files from that single point instance. For simple models like the Turbojet, this is not needed, but for more complicated jet engine models, this would aid the solver to converge quicker. And again, there's an option here to store a fully initialized model so that you don't have to reuse these result files again and again. So I've already ran this function again, and the result here is this model that's fully initialized. Again, everything here is the same, except that this one has better initialization because it used the result file from a single point simulation. And if I want to now simulate this model, I can just simulate this as a normal steady state simulation. And I then click on the simulate button to compile and then simulate the model. So again, the first step is compilation, where the Modelica code is compiled into a binary algorithm. And since we have 3 instances of the Turbojet model, this compilation is going to take us a few more seconds compared to our Turbojet model that we first compiled. But once the compilation is done, the simulation should be very quick. So here we have our result file again. And now let's look at a result. So since we targeted an overall pressure ratio of 6 for the cruise, let's make sure that we actually achieve that. So I can filter variables by selecting a component on the canvas and also by typing in strings in the search bar here. And now I can see that there is a summary variable called OPR for overall pressure ratio. I can make a plot for this by dragging it onto the canvas. And if I hover over this, it is actually our target value of 6. So that is a quick example of the multi-point workflow using a Turbojet. Now let's take a look at a slightly more complicated turbofan model. So I'm going to be utilizing an example in the jet propulsion library. The starting point again is the same. We have a baseline model. And here you can see that this is a typical turbofan setup. We have our main flow flowing through the compressors and the turbines. And then we have a bypass flow just going out the nozzle. And once we have the baseline model, we introduce some control logic for the burner. And then using the control model, we do multiple single point simulations and save those results. Then we expose the inputs that we need to control externally to the top level. So, excuse me. Here we can see that there are 3 operation synthesis variables and 6 sizing synthesis variables. And again, the next step is to generate our submodels using the function from JPL. We provide our design submodel name and our off design submodel names here. in this particular case, we use top of climb as our design point. And once we generate the submodel, we are again presented with how many ever instances we chose from that function. So here, if you look, we have our on design point, our on design submodel TOC. It's got the sizing inputs here exposed, and then off design cruise submodel at cruise flight conditions. Michael also mentioned that there are two schemes for the multi-point approach for the turbofan. We have both available as examples in the library. But for today, I'll be focusing on the Cranfield approach. And if I look at our initialized model here, actually, let me go back here and explain that one more time. So when we first simulate our multi-point model where we have the control logic implemented or the closure equation, so to speak, the first time we simulate this model, we'll again use the JPL function just with mapping to the single point result files. And again, this would better initialize the model and help the solver converge faster. But we also have an option to save the initialized model, which would then result in this model called table 11 initialized, for instance. And this model is independent of the single point result files. It can be simulated using the standard standard steady state solver in Impact. And let's try to change one of these parameters here for this model. You can see that this one's grayed out, and that's because this is an example from the library, so I cannot make changes to it. And if I wanted to make a change to it, I would just duplicate this to my workspace package, which I've again done for today's demo. So I'll open up the duplicated model here. And the model, I can make changes to. So say we want to target an overall pressure ratio of 50 for our cruise conditions. I can provide that input here, and then I can just simulate this model in steady state mode. So I'll go ahead and simulate. Again, the first step here would be compiling the Modelica code into a binary algorithm. And we have 3 instances of a fairly complicated turbofan model. So the compilation might take a few seconds here, but once that is done, the simulation should be very quick. So I'll just wait for this to finish, and then we can look at some results. And there we have our result. So since we're targeting the overall pressure ratio again, let's first make a plot for the overall pressure ratio. I can do that by dragging it onto the canvas. And it is indeed 50, which was our target value. And now let's look at what the input had to be for this target value to be achieved. So I'll select my on design instance, top of client, and I'll plot the overall pressure ratio again. And here we can see that that input had to be 61.24. So instead of you manually having to iterate on this input here, the solver did that hard work, or the redundant cumbersome work for you. So that was all I wanted to show for this portion of the demo. And the next one is really looking at a web app and how that enables customization and collaboration through Modelon Impact. So the tool I've been using, it's called Modelon Impact. Since this is a technical seminar, I won't be going into too much detail about what features are available in the tool. But one thing I want to highlight is how it enables collaboration. So Impact has an API, which lets you leverage that and build customized views. So here I can click through the UI and open a customized view for the same turbofan model. So this one is customized because it has a single input that can be set using a slider here. And the idea here is also to simplify the model so that non-experts don't get overwhelmed by all the parameters that are available through the model. So web apps allow customization because you can control what the layout looks like, but it also enables collaboration. So I reach this web app through the UI, but I can equivalently copy and paste this URL and share that with my colleagues, and anyone who has the URL would be able to reach the web app. So I think this is a good time for everyone to access the web app and just follow along, and we can do a quick simulation and see how that works. So Jocelyn, can you share the link to the web app in the chat window, please?
Yes, thanks, Madan. I actually just realized that the chat feature within the Zoom webinar is turned off, so I'm not able to share it through the chat window. However, I have just sent an email to all of the registered attendees with the link to the web app. So I do apologize for this inconvenience. It was an oversight on my part. So if you check your email quickly, you should be able to access the live web app there. I've also answered one of the recent questions. I'm not sure if you're able to see it, but I included it in the link as well too there.
Thanks, Jocelyn. So while I can wait a couple of minutes so that everyone has the link, and while you get the link and you open it, I also want to say that we got an overwhelming response to the webinar, and this is the first time that we are trying a web app with so many people clicking at the same time. So what's happening behind the scenes is that there is a cluster running with some hardware specs, and when you click on the simulate button, that simulation request is going into a queue. And since we have a lot of people today trying to simulate the model, there might be some queuing happening. So some of your simulations might take a little longer, and that's expected, but hopefully it doesn't take too long. So I'll wait another minute maybe, and then we can go through the web app and try to plot some results.
Please let me know in the Q&A if you have not received the email with the web app, and I can reply with the link as well too.
Did you get any comments in the Q&A section, Jocelyn? Are we good to go?
I have not. So
Okay.
we'll address all questions regarding the application and questions from Michael and Madan at the end. But please let me know if you have not received the link to the web app. Thank you.
So there was one question which we've replied such that it's visible to everyone. So I hope we're ready to go.
Okay, awesome. So what this web app does is just expose one parameter, the overall pressure ratio, and there is a slider that you can use to set a range of values for that parameter. So the step size here for this particular web app has been hard-coded to be 1. So whatever the range is, the step size is going to be 1. So if I do 49 to 51, I have 3 values for my overall pressure ratio, 49, 50, and 51. So once you've chosen a range using the slider, you can just hit simulate, and that should just give you a plot with some key performance indicators. So looking at the plot, we have 4 variables that we are trying to monitor or visualize here. So the thrust, the specific thrust, the specific fuel consumption, and the burner outlet temperature. And the 4 lines are color coded. So the red one here is our specific thrust, and we have our outlet temperature for the burner, the specific fuel consumption, and the thrust again. One thing I want to highlight is that there are 4 different axes, so there are different scales for the different plots. But then it's also important to note that the thrust is actually not changing. It's fixed, and that's why you see a constant line. And the axis here, if you look at the units or the range, it's actually the same because that one is fixed. There's also a drop down here, so you can look at the other submodels or flight conditions. So if you want to look at cruise, you can just select cruise. If you want to look at top of climb, which is our design point here, you can look at top of climb too. And again, if you want to change the range and simulate the model again, you can just use the slider and hit simulate again. And that should take a few seconds and give us a new plot. So that concludes everything I wanted to demo. So I'll pass it back to Jocelyn for questions.
Great, thanks, Madan. So we did receive a few questions. We will allow just a few more minutes for people to access the web app and perhaps play around with it and come to the table with any questions that you may have. There were a few people who said that they did not receive the email, so I apologize about that. Thank you, Michael, for responding. So let me get into, just give a few more minutes for people to use the web app.
Yeah, I just want to say that we can have the web app available for some time even after the webinar. So feel free to click along, even if you didn't get the link right now. Apologies again, but we'll keep the web app running for some time so that you do get that experience.
Thank you, Madan. Okay, so we did receive one question, and this is in regards to the multi-point design approach and designing a component for multiple operating conditions. The question is this restricted to the jet propulsion library? So that would be a question for Michael.
Yeah, I can certainly take that one. So no, the methodology is not at all restricted to jet engines. We also apply this for electric power systems, hydraulic actuators, and so on, where you need to ensure that the design satisfies certain conditions across the whole mission, really. That said, the particular, we call them custom functions that Matun showed in the demo, they are specific to the jet propulsion library, but other ones can be developed for other libraries based on what the customers need.
Great. Thanks, Michael. So there were several questions that came in about the web apps. And I'll relay these to Madan. I would say would be the best person to answer them. The first question is, how do I create my own web apps like the one shown?
Yeah, so a web app is essentially a combination of 2 files. It has a JavaScript file which controls what happens when you click something. So for instance, what happens when you drag the slider or click this button. And then it also has an HTML file which controls the layout of your web app. So The answer here is depends. There is a little bit of learning curve involved for like learning HTML and JavaScript, but that is something we can help with. And then Impact also has a convenient API client. So what is happening behind the scenes here is I'm using the Impact API and interacting with Impact using JavaScript. So we provide the API and also a JavaScript wrapper client, which you can leverage in your JavaScript code to build web apps. But there is a little bit of learning curve with learning JavaScript and HTML, but we, from our side, can help with developing web apps. And our commercial team can provide more details. So if you're interested in using Modelon Impact and building web apps for Impact, feel free to reach out to us.
The next question in regards to web apps was, do you need a full Modelon Impact license to use one of these web apps?
That's a good question. No, so Impact was designed with the principle that model utilization should be maximized. So building models is always an investment, and we want to generate more bang for the buck. And web apps really help non-experts also, simulate models and get results out of them. So running web apps does not require a full license, which is what you would need to access the UI. It requires something called a deployment license, which is lower in cost. And again, specific details regarding pricing can be communicated with you by the commercial team. If that is of interest, please reach out to us.
Great. And then one of the last questions from Adin would be, can anyone with the link access the web app?
That's again a good question. The answer is it is configurable. So if you want to design a web app for, say, customers, and you're like a vendor providing a certain system to a customer, you might want to enable an anonymous user access, meaning anyone with the link can access that. But there's also the option to allow only logged in or authenticated users access to web apps. So it is configurable. And again, the API does provide the functionality for that.
Great. Thanks, Madin. Okay, so one question that just came in was, after simulation, the thrust is constant value, but physical running case, it will be a variable value. Could you please elaborate?
Can maybe take that one.
Yeah, Michael.
So that's a really good one. So there are two parts that we distinguish for the results that you see here. We look at different operating conditions for the sizing, so to decide how the cycle should look like, how big or small to make all the components. And there we deliberately ensure that the thrust doesn't change when we change any of the other variables, like your design point pressure ratios or your combustor outlet temperature. Usually they would introduce some bias there. But as we want to answer the question, what choices do we have to satisfy a requirement for a certain aircraft? The thrust level is supposed to stay constant, so that we can ensure this apples to apples comparison. If we say the engine with a higher overall pressure ratio also generates more thrust, well, then we wouldn't be comparing really appropriately there. And then the other aspect of your question is that we can always run the sized cycle, the Aero engine, to different thrust levels by increasing the fuel flow, fuel to air ratio, etc. So we can throttle it up or down. But that's kind of then a second step after the design that we're looking at here. Hope that answers the question.
Great, thanks, Michael. One more question that had come in prior to today's webinar was, about creating your own blocks from multi-point synthesis, like the bypass ratio from velocity ratio example, and then also the code editor and Modelica being used for all of this. I think that one's for Michael.
Yeah, maybe Mitsuni, you can also show it along while we talk about it. So yes, you can definitely create your own variants of those. You can look at the ones in terms of the equations that we use. You can create your own versions of that. All of this is based on the standardized Modelica modeling language. And yeah, it really allows you to create your own in-house, even a bit like in-house software on top of this modeling language, because we have these hooks from object orientation to drop in your correlations. You can edit the code, create your own variants, your own way to parameterize models, etc. So this is certainly possible, not only for these blocks, but even the whole modeling of the gas turbine, the electrification components, or whatever other parts you're interested in. And yeah, here is the code editor in Modelon Impact that Mithun's showing.
Great, thanks. There was one question that came in about learning this software. Are there any free version or classes? At this time, the answer to that is unfortunately no. There are of course certain special circumstances where we do offer, perhaps an academic license, but I think that at this point, that's something that our commercial team would have to answer, and what we can do is follow up individually after this webinar. So if you do have questions in regards to licensing or purchasing a license, yeah, please feel free to reach out to me, and we will also follow up directly after this webinar as well too. So there was one more question that just came in. Is the simulation process calculating some mathematical optimization solver or just simulating the model? That's probably Michael.
So yeah, again, we will also take that one. So the examples that we're looking at right now, they use simulation or satisfying the equations like a nonlinear algebraic solver. We also have functionality in the underlying Modelica compiler to handle optimization problems. But the examples that you're seeing here now today, they use, in inverted quotes, just simulation.
Great. Well, I think we have answered all of the questions, as I know. So if there are any other questions that may arise that you after the conclusion of the webinar that you think of, always feel free to reach out to myself or Michael or Madin directly. I believe our emails, or my email specifically, is on the webinar. So again, please feel free to contact me directly, and I will send your email or your question to the appropriate resource internally. So thank you so much for everyone for joining today's webinar, and I hope you found it insightful and you were able to learn something, and that will conclude today's webinar. So thank you. Have a great day.
Thanks, everyone.
Thank you.
Thanks.